Hi, the topic of today's lecture is linear maps from Rm to Rn. I had already given a lot of lectures on linear maps in linear algebra. I think about 10 or 12 lectures we had given on that. So what I am going to do is some kind of a summary of various things, but with complete details in a very short way. These lectures were based on my talks to some of the students, not students I would say, employees in who work in data science. Okay, and I found that to be easily accessible to BSc level students, because I have seen students who have gone through various linear algebra course even after MSc. They don't have a very concrete idea about how to look at linear maps from Rm to Rn in a very concrete way, explain it to others. So this may be of use. Okay, right. Let me screen share. Let me see whether everything works fine. Yeah. So let me just make sure it's a screen share. Yeah, right. So we are going to start with the simplest case, namely what are all the linear maps. Suppose F is a linear map from R to R. Right? This is the first thing I want to look at. I want to find all linear maps from R to R. The secret is, whenever you want to look at, okay, look at the action of the linear map, that is the image of the linear map if you want, on a smartly chosen basis. Basis of the domain. Okay, this is going to be running trick. Okay, now for R it's a one-dimensional vector space, therefore I can take the basis to be consisting of one element. Therefore if you give me any real number x in R, I can think of this as a one-dimensional vector, therefore I can write it as x times 1. Here I think of this as a vector, here I think of this as a scalar. Right? Therefore if f is a linear map, then f of x is going to be f of x dot 1, therefore it's x into f of 1. Suppose I let a equal to f of 1, then I can write it as a times x. Right? So what have you found? If f is a linear map from R to R, then it is necessarily of the form for all x in R, f of x is equal to a of x. And do I know what is a? Yes, a is the value of f at 1, because you just put f at 1, then you get a. Right? Okay. Now, so if f is linear, we got f is of the form, but we do not know whether fx equal to ax, the map defined by fx equal to x, is whether it's linear. That is very easy. This is all just a linear, the distributive property of real number system, that is ax plus ay, which is a times, so this is a down, sorry, ax plus ay. Therefore this is going to be ax plus ay, that is going to be f of x plus f of y. And similarly for t in real, f of tx will be a times tx, but commutative will tell me this is t times ax, that is t times fx. So what I have shown is that this is linear. So what we have shown now, we have shown two things. Fix a real number alpha in R, define f of x equal to alpha times x, then this is linear from R to R. Conversely, any linear map from R to R is of the form f of x equal to ax, what is where a is f of 1. Here also you see that f of 1 will be alpha. Okay, please, therefore we arrive at the following lemma. Okay, any linear map f from R to R is of the form f of x equal to ax, where a is f of 1. Okay, so we have found all the linear maps. Okay, You will be surprised. This is never discussed in many books, etc. Of course, my book deals with. Yeah, I forgot to say the reference or linear algebra book of mine, and then based on my discussions with, as I said, with some group, I typed it as linear maps from Rm to Rn. It will be uploaded to this place. So after a week or so, you may be able to download it. Okay. So pause, review, proceed. Right. Now next thing is I want to look at linear maps from Rm to R. Right. So let's go to the secret recipe. What is the secret? Look at smartly chosen basis of the domain and look at the action of the linear map. So what is obvious? The basis for Rm. So I will think of Rm as column vectors. Usually in algebra we will think of as a row vector. The reason for row vector is it is easier to type, otherwise it takes a lot of space. Okay, if I write as a column, that's one of the reasons why we take, right? But in general it's easier to think of this as a column vector. Okay, therefore let x, I will write it as x1 to xn, x1 to xm, but I may write it like this, but what I mean is this. Okay, it's a transpose. Okay, even when I write x1 x2 as a row vector, please think of it, I think of it as a column vector. Okay, for expediency I'm just writing as a row vector, right? Okay, therefore what is the basis then? This basis is ei, where 0 0 1 okay, 1 and 0, that is 0 1 0, where 1 occurs with the ith place, right? Therefore any vector x I can write as x times e1, x1 times e1 plus x2 times e2 plus xm times em. Right, just look at this. Yeah, right. So since f is linear, then I know what is f of x. F of x is going to be f of this object, but remember f is linear, therefore it's additive. Therefore f of x1 e1 plus f of x2 e2 plus f of xm em, but it's also linear, therefore it's equal to x1 times f of e1 plus x2 times f of e2 plus xm times f of em. Is that okay? Now let me denote ai equal to, define this f of ei for 1 less than equal to I less than equal to m. Then I can rewrite f of x as a1 x1 plus am xm, where what is ai? Here also I know what is ai. ai is nothing other than f of ei, right? When I take x equal to, let's say x equal to 1 0 0, that is e1, when what will happen? a1 times 1 plus a2 times 0, am times 0, therefore I will get a1. So similarly I will get ei. Do you follow that? And notice that this is linear. Okay, if you fix any m coordinates, okay, real numbers like this, and define f of x equal to alpha 1 x1 plus alpha m xm, then f is linear. Then f is from Rm to R, this is a linear. Okay, again it's very trivial to check, that is going to be alpha times x1 plus y1 plus alpha m times xm plus ym. This is exactly similar to what we did, alpha 1 times x1 plus alpha 1 times y1 plus alpha m times xm plus alpha m times ym. Then what do? I club these things together, and I club these things together. Okay, so I will get something like etc. Okay, similarly scalar multiplication. Yeah, So what do you think we have proved? So we have proved that if f from Rm to R is linear, implies, okay, there is this scalars a1 to am in R such that f of x is of the form a1 x1 plus am xm, and I am not simply saying there exists a1 atm, but I know what they are. They are nothing other than, my a is nothing that f of ei. Okay, so this is the second lemma. Okay, pause, review, proceed. So Yelly linear map from Rm to R is of the form f of x equal to a1 x1 plus a2 x2 plus am xm, and what is a1? The value of f at e1. What is am? The value of f at em. Okay, alright. Okay, now let's just have a slight digression. So as I said, this was lectured to some of the engineering students who are working in data science. Therefore on Rm we have what is called the dot product, right? If I had two vectors x and y in Rm, then x dot y is defined to be x1 y1 plus xm ym, right? Now in view of the dot product, you can see lemma 2 can be written, okay, like following. Okay, if f from Rm to R is linear, then there exists a vector a equal to a1 to am in Rm such that f of x is a dot x, where a is nothing other than f of ei. Do you follow that? So I am simply rephrasing the earlier thing in terms of assuming that you know dot product. If you don't know dot product, you can ignore, no problem. Okay, right. So let us quickly recall what have we achieved now. We have shown that we have characterized any linear map f from Rm to R, right? But what did you want? We wanted linear maps. Now I will choose T, a linear map from Rm to Rn. Okay, we want to study this. In fact, we want to find all this. All. Right? Now what do you do? Okay. See, this is where the mathematics comes. I want to look at linear maps from Rm to Rn, but I do not know how to do that, but I know how to find linear maps from Rm to Rn, right? So this suggests, okay, given a linear map T from okay, let us look at Rn. Okay, let us look at Rm to R. Can you think of linear maps? Simplest linear maps. Okay. See, remember, f of x, any linear map f is given by a1 x1 plus am xm. So suppose I take a1 equal to 1 and ai equal to 0 for I greater than equal to 2, then what do I get is f of x equal to just x1. That is, if I have x1 x2 xm, okay, I am dropping it only to x1. Similarly, if I have xi, I drop it only xi. These are called the projection maps. So let me call pi I is a projection from Rn to R, where pi I of x1 to xn equal to xi. That's the ith coordinate of x. Okay, and then pi I is linear. This is very easy to check, because if you give me x plus y, then it is x1 plus y1, x2 plus y2, xn plus yn. Therefore pi I, the ith coordinate of that will be xi plus yi, but that is pi I of x plus pi I of y, etc. Do you understand that? It is easy. Okay, right? But let's go back. Lemma 2 we characterize by saying, we reformulated by saying any linear map f from Rm to R is a form f of x equal to some a dot x, where a is a vector in Rm. And we also know what is a. A is the thing as an f of a. Do you understand that? So now you say pi a is a linear map. Pi a is a linear map from Rm to R. Okay. So therefore, what is the vector a? You see that pi a of x nothing other than x dot a, because I have x1, xn, and here I have, this is xi, here I have 0, 1 at the ith place, and 0, this is 1 at ith place. Therefore the dot product is going to be just xi. Do you understand that? Yeah. Therefore the pi I, the Rn to R is the ith projection, is a linear map. Okay, that is pi a of x equal to xi, and it's also given that x dot ei. Okay, so this is third observation. Okay, so this is a, if you want, third lemma. So what did the third lemma say? It told you how to generate projections, right, from Rn to R. Okay, now come back to our next one. This is a very general observation. Suppose U, V, W are vector spaces. Okay, and U to V, let us call it A, and V to W, let us call this. These are linear maps. Then I have the composition B composite A. That's a map from U to W. So how is it given? B composite A of X equal to B of Ax. Now where does Ax? Ax is in B, and B is from B to W, therefore this is going to be in W. This object is in V and B is from B to W, right? So this is a linear. B composite A, if A and B are linear, this is a linear from U to W. Okay, let us quickly do that. B of A of, let us say, x plus y, where x and y are in U. Okay, this is by definition B of A of x plus y. But A is linear, therefore it is B of Ax plus Ay. Where are they? These are in, this is in B, this is also in B. And B is from B to W linear map, therefore this is B of Ax plus B of Ay, but that's nothing other than B composite A of x plus B composite A of y. Therefore this map is additive. And similarly scalar. So what have we shown? This is linear. Okay, pause, review, proceed. Okay, now come back. So now I want to understand linear maps from Rm to Rn, right? Okay, now what I said was, if I do not know linear maps from Rm to Rn, but I know linear maps from Rm to R, that we have classified by lemma 2 and lemma 3. Do you understand that? Right? Okay. Therefore, given T from Rm to Rn, can we get naturally, in a natural way, linear maps from, call it Ti, from Rm to R? Now let's look at just now what I did. Please think, what was the last two results we did? The last result said composition of linear maps, and just before that I said there is a obvious linear map from Rn to R, which is the projection. So if you combine these two, you should be able to give me a n linear maps from Rm to R. Given T a linear map from Rn to Rn, you should be able to give me n linear maps from Rm to R. How will you do that? So I have Rm to Rn, this is T, then I have the projection pi I, which is a linear map. This is projection is for I 1 to n, right? Therefore if I define Ti equal to pi I composite T, then that's a linear map from Rm to R. Why this is a linear map? Because pi I is linear, we have seen T is linear, composition of linear map is linear, therefore you have found that. Do you understand this? Now I am in a familiar ground. Okay, what is a familiar ground? I wanted to look at linear maps from Rm to Rn, but I reduced the problem to linear maps, n linear maps from Rm to Rn, and I know how to write them. Is okay? Please marvel at this. See, linear algebra is not just simply reading theorems and learning the proof by heart. You understand this? You should have the kind of, you should be able to feel it and work with it. Okay, be confident. This kind of thing will help you there. Okay, right. Now, how does pi I, so let me write Ti, therefore from Rm to R, how will it look like? So Ti of x, remember it should be something like a1 x1 plus am xm, but remember this a1 a2 am will depend upon your I, Ti, therefore I call it as ai1 x1 plus aim xm. Okay, therefore there exists ai j 1 less than or equal to j less than or equal to m, and this is true for all I between 1 and n. Okay, Ti how many are there? 1 less than or equal to I less than or equal to n, because there are n projections pi I from Rn to R. Okay, these are 1 less than or equal to I less than or equal to m. You follow that? Okay, so we found out what is T. Therefore if you find T, okay, I have found out Ti of x. Do you understand this? Yeah, but what do I want? I want T of x. T is a linear map from Rm to Rn, but what you have told me is what is Ti of x. This is known. How do I get T of x? But that's very easy. How do I do that? Call Tx, so this is a vector in Rn, and x is a vector in Rm, and T is a linear map from Rm to Rn, right? Now, so I know y. To know y is same as knowing yi for less than or equal to I less than or equal to n. That's the ith coordinate of yi. You understand that? Yeah. But how do I know yi? Remember, yi is nothing other than the projection, and yi is nothing other than the pi I of y. What is pi I? Pi I is the ith projection from Rn to Rn to R. But what is y? This is pi I of T of x, but that is pi I of composite T of x, but that is your Ti of x. Are you following? Please go through. This is the kind of thing you should feel it. Don't worry about trying to remember these things. Try to follow, try to think along with me. Okay, and again rewind and see. You will see how easy it is. You should be able to do it on your own. Okay, therefore my y, which is T of x, we found it is T1 of x, Tn of x, right? But what is, I know what is T1 of x, that is a11 x1 plus a12 x2 plus a1m xm, and here an1 x1 plus an2 x2 plus anm xm. Just go through this. What is TI of x? ai1 x1 aim. Therefore, okay, t1 of x is a11, tn of x is an1 into. Do you follow that? So you found it. Yeah, right. I don't know why the light has gone down. Yeah, right. Therefore, I found out what is tx. Tx is going to be this vector, right? But notice that, okay, if I write these things a11, a1m, an1, anm as a matrix and multiply this x1, x2, xm, this is an n cross m matrix, this is m cross 1 matrix, that's what will give me y1, y2, yn, that is n cross 1 matrix which is in Rn. This vector is in Rn. Yeah, try to think what we have done. Therefore, okay, what have we done now? This quite, we have done quite a bit. What did we do? If T is a linear map from Rm to Rn, okay, then we found T of x is nothing other than pi I composite, pi 1 composite T of x, pi n composite T of x, but that is equal to, we wrote down this matrix, this is going to be a1 I xi I equal to 1 tm and summation a ni xi equal to 1 to m, and which is same as a times x, where I call this matrix as a. Right? So what have we done now? So this is the theorem we have proved. Okay, if T from Rm to Rn is a linear, then there exists an n cross m real matrix, of course, A such that T of x equal to Ax. Okay, but now take any matrix, an n cross m matrix, and define T of x equal to A times x. Is this linear? We said if it is linear, it is of this form Ax. Yeah, the matrix A times the vector x, right? But is it linear? It is always linear. That's what we want to say. Why? That is very easy, because that follows from the matrix multiplication A of x plus y, but this is Ax plus Ay, etc. And T of, okay, lambda x is A lambda x, but that is lambda times Ax, that is Tx, right? Therefore, if T from Rm to Rn is linear, it is given by Tx equal to A times x, where A is n cross m matrix. Now, if you had been following our earlier things, lemmas 1, 2, 3, 4, etc., whatever it is, you should ask for one more extra information. It is not only the matrix A, but we know the matrix A, that is, we know the matrix entries, the entries of the matrix A. For example, let us look at f of x equal to Ax. If f is linear from R to R, we said fx equal to A times x. Okay, it is of the form A times x, where A is a real number, but we know what is A. What is A? A is f of 1. And similarly, if f is a linear map from Rm to R, then we found any linear map should be of the form fx equal to a1x plus a2x plus a2x2 plus amxm, and I know what are A. A is nothing other than f of A. So it is not only there is a matrix A, I know the matrix, the entries of A. So how do I do that? Let us go slow. Okay, that the thing. Please, this is a way, it's never taught. So it's if you simply look at linear algebra as some kind of writing, You will be surprised. Okay, getting all these facts together will make life easy. You will feel confident how to work with matrices and linear maps, interchange them at any time. You can do that. Okay, so how do I do that? Let us look at. So suppose, let us look at my matrix A was A11, A12, A1M, right? And here AI1, AI2, AIM, and similarly AN1, right? Now how do you think I will get AIJ? Remember this AIJ, what was that? That was nothing other than you write TI of X as AI1 X1 plus AIM XM, right? But what is my TI? TI is a linear map from Rm to R. Okay, therefore these are the coefficients of the linear map that I know what they are. What is that? That is TI, okay, of this one. If you want to call it EJ, that is your AIJ, right? Remember, if f is from Rm to R, if I write f of x equal to A1 x1 plus AM xm, and what is my AJ? AJ is nothing other than f of EJ. You understand? So this coefficient, jth coefficient, is given by T of EJ. Are you sure you follow that? Very good. Okay, therefore I know what are all the coefficients, but I know something more. What do I know? Something more. Remember, T of EJ is nothing other than pi I of TJ. So that is AIJ, right? Okay, but what is pi I? Remember, pi I is from Rn to R, and that's a linear map. We know that pi I of x is nothing other than x dot EI, where EI is the standard basic vectors in Rn. Don't confuse with this and that. These are all something. Okay, if you want, let me call it as UI. Okay, the standard basic vector in Rn, right? Therefore pi I of T of Ej is nothing other than T of Ej dot product with UI. But this is nothing other than my AIJ. Pay attention. Therefore the matrix A, I know it is AIJ, and AIJ is nothing other than, to look at the linear map, and that is a linear map from where to where? Rm to Rn. What are the standard basic vectors? I denote by EA, okay, and EJ if you want, and I denote this standard basic vectors of Rn by UI. These are all standard basic vectors. Okay, this is an n tuple where one appears in the ith place. Therefore that AIJ, how do I get? Look at T of EJ and take the dot product with UI. That's it. Okay, therefore the theorem says something more. If T from Rm to Rn is a linear, then okay, T of x is A of x, where A equal to Aij, and what is Aij? Aij is, look at T of Ej dot with UI, where E1 to EM standard basis of Rm and Rm, and U1 to Un standard basis of Rn. Yeah, so do you see that we have now found all linear maps from Rm to Rn. Okay, and if you have been going through your standard linear algebra course, you may find that I went fast, but remember, I always give you a chance. Pause, review, proceed. So you pause, review it. Okay, and Once you are done once, go through the entire video second time, then close it, try to think on your own. You will find it much easier. Okay, there are few more remarks which I want to talk about. I will say that also. Okay, but let us summarize. What was our plan of attack? The plan of attack was, first we wanted to find what are all the linear maps f from R to R. What did we find? They are of the form fx equal to a times x, where a is a real number. Do I know the real number? Yes. If f is linear, that a is nothing other than f acting on 1. Right? Conversely, any linear map which is defined by fx equal to alpha times x is linear. Therefore, any linear map from R to R is of the form fx equal to ax and a is f at 1. That's first lemma. Second thing is, we extended the same argument to find out all linear maps from R and Rm to R. How did you find? Again we said f of x is the form a1 x1 plus a2 x2 plus am xm. And what is ei? It is a linear map f acting on ei. Right? So we classified. And the third thing, what did you do? We looked at a special case of this lemma 2. We defined the projection maps from Rn to R, pi I of x equal to ith coordinate of x, namely xi. Okay, that's a linear map. Therefore, it should be a dot product with a vector. We found out pi I of x is nothing other than x dot ui, where ui is u1, u2, un is the standard basic vectors of Rn. I just changed the notation from what I wrote in the lecture, but this is it. Okay, and this is the third. What was the fourth one? Fourth one was composite of linear maps is linear. Using that, what did we do? Give me a linear map T from Rm to Rn. We produce n linear maps from Rm to R. Those linear maps we know how to deal with. Okay, so that is the last part. Okay, you go through again so that the notations will be easier for you, because many of you will be intimidated by the notation, but if the concepts are clear, you will see what it means. So how did I get Ti? Ti is pi I composite T. That is, take x from Rm, look at Tx which is vector in Rn, and project it to its ith coordinate. Therefore I get pi I of Tx. Okay, that I know how to write, because that's a linear map from Rm to R. Then I know how to write it. Okay, that's how I found out Aij. Okay, right. Now there are a few more things which I will explain and stop the lecture. Okay. Now look at f is from linear map from Rm to R. Okay, it is of the form f of x equal to a1x plus amx. Okay, notice that x1 xm. Notice that this is a first degree polynomial in the variables x1 to xm. Okay, but when I say first degree polynomial, there could be a constant term, but what we found is that without constant term or with zero constant term. With the constant term equal to 0. Right? Therefore, any linear map from Rm to R is a first degree polynomial in the coefficients x in the variables x1 to xm. Okay, that's the first thing. Right? Are you following? And that is also given by dot product with a vector x dot a. Okay, right. Therefore, if I give you a function something like that, f from, let us say, R3 to R, that f of x, y, z equal to, let us say, 5x minus 3y plus z, 2x plus 6z, okay, and something like y minus z plus 5, okay, oh sorry, from R, right, so it should be only one, 5x minus 3y plus z. I know this is a linear map. If I give 2x plus 6z, I know this is a linear map. But if I say the f of x, y, z equal to y minus z plus 5, this is not a linear map. Why? It's a first degree polynomial in x, y, z, but constant term is 5, right? And similarly, if I give something like f of x, y, z equal to, let's say, x squared plus y, okay, this is not linear. Why it's not linear? Because It's a second degree. It's actually third degree polynomial if you want, if combined degree, but it's not a first degree polynomial in xyz. Therefore, this is not linear. Okay, and similarly, if I say f of xyz equal to cos h of xy, again not linear. See, so easy, right? Now let's look at, suppose I want you to give me a linear map from let us say R4 or let's say R3, R3 to R2 linear map T. How will I give? Remember, we know T of xyz must be, let us say, P1 of xyz and P2 of xyz, because this is your T1 of xyz, the first coordinate, right? This must be first degree polynomial in xyz. This must be again first degree polynomial in xyz with zero constant term, right? Therefore, I can simply write it. There is no problem, right? I will write it as 3x plus 4y minus 5z, and this is minus x plus 21y plus 30z. That's it. Okay, you don't have to verify. You know these are going to be linear maps. Are you following? Yeah. So please go through these things. My article actually does a little more than this, but I think there's already enough time, so I will stop here. But this alone is worth going through twice. You will be very confident how to deal with linear maps from Rm2Rn, and especially if you go to some kind of places, applications of linear algebra where you need some kind of numbers, matrices, etc., floating numbers as data scientists would call. Okay, you have to learn how to look at linear maps Rm2Rn very concretely. You should have an intuitive feeling, and you should also know how to work with it. Hopefully this lecture would help you. Okay, we will meet again.